This is easy because 0 plus 1 is 1. Log of 1 is always 0. Log in any base of 1 is always 0. How do I know? A raised to 0 is 1. A raised to 0 is 1. So when t is 0, log of 1 is 0. 0 times negative 18 is 0. 76. That's the average score. In part B, after 2 months, after 4 months, after 6 months, 8 months, and 1 year. Okay, when I see that, I will immediately create a little table. The table is always self-explanatory. If I have all this information on pages and pages and pages, it's more difficult to draw conclusions. So I have t, I have f of t, I already have the 0, and they want 2, and they want 4, and they want 6, they want 8, and they want 12. Of course, you have to put the function in the graphing calculator. You're not going to calculate these by hand or step by step for all these numbers. It's a waste of time. So 76 minus 18, common log of t plus 1. Put the function in right away and plug in all these numbers in a blink. 0, we know it's 76. And then they want 2, and they want 4, and they want 6, and they want 8, and they want 12. All I have to do is just copy them, go back, and just highlight. Okay, 67.41. The next one, 63.42. The next one, 60.79. The next one, 50.82. And after a year, 55.95. So much easier from 76 to 67 to 63 to 60 to 50 to 50. No, no, no. No, no, no. $58. Okay, 58. Yes. Okay. So 76, 67, 63, 60, 58, 55. Okay, makes sense. Next question. Use the results from part A and B to graph. Describe what the shape of the graph indicates in terms of the material retained. Okay, very good. So I already have the function in the graphing calculator. Now I have to select a viewing window. So x is between 0 and 12. It happened that we did something similar last time with a scale of 2. The y minimum from all these numbers, the y minimum is somewhere about 50. The y maximum is 76. So the minimum value for y should be 50. The maximum value for y should be 80. Because I know the answers, I have the answers. So 50 and 80. With a scale of 20, that's fine. And now I want to graph. Aha. So the function is decreasing. It starts with 76, and in a year it drops to about 56 average score. So that's the graph. Any questions, please? Okay. Let's move on. Here it is. Find the domain of each logarithmic function. So let's choose 41, 42, 43. we know how to find the domain because in all logarithmic equations we stated the domain, but we need to practice again. So 41, 42, 43. Find the domain.
Can we do 43?
Yes. In 43 we have f of x equals natural log of x minus 1 squared. Perfect. You can say, what is the domain here? This is always positive. So you're done. Not exactly. This is indeed positive, but it could be 0. So x cannot be 1. How come? Well, 1 minus 1 is 0, and we just looked at the fact that natural log of 0 does not exist. So everything goes except 1. So the domain of this function is negative infinity to 1 union 1 to infinity. So this problem is a little bit tricky because they are throwing this at us. And we know that the quantity that log is applied to has to be positive, but it can never be 0. Now, if they do something else, like let's say f of x equals natural log of x squared plus 1 squared, this is always positive and it will never be 0 because x squared plus 1 can never be 0. This is positive plus 1, never 0. We know that this has imaginary solutions. So for this one, yes, the domain is everything, but not for this one because it can be 0. So this is a little bit tricky. Good pick. Good. Any other domain? Do we need another domain or not?
Yeah, 41.
Yes, let's do 41 as well. Very good. 41, f of x equals log base 8 of x plus 5. This is a nice one. No trick here. They're not trying to trip us in any way. This has to be positive. So x plus 5 greater than 0 or x greater than negative 5. So domain negative 5 to infinity. The x plus 5 shifts the graph 5 units to the left. So that's why the domain is negative 5 to infinity. Without the 5, the domain would have been 0 to infinity. Good. Write each equation in its equivalent exponential form and backwards, and evaluate without a calculator. So 13 through 29.
We do number 13.
Of course, let's start with 13. Very good. In 13, we have 1/2 log base 49 of 7. So let me refresh your memory on this conversion. Okay. Log base a of x is y is equivalent to a raised to y equals x. You should have this in your notes, and you should write it many, many times so you don't forget it. All I have to do is get this set up look like this. Log base 49 of 7. Log base 49 of 7. equals 1/2. This raised to this equals that. 49 raised to 1/2 equals 7. Is it true? Yes. The square root of 49 is 7. Is this okay?
Yes.
Perfect. Anything else from 14 to 29?
Can we do 22?
Yes. Let's look at 22. Good. In 22, we have log base 16 of 4. Now you see that these are a piece of cake based on where we're coming from section 4.5. Good. I have no idea what this is. But I know I can change it. 16 raised to y equals 4. Again, this is a piece of cake. How do I know? Because 16 can be presented as 4 squared. So then 4 squared raised to y equals 4. Or 4, copy the base, multiply the exponents, equals 4. And now we already know if two exponential notations with the same base are equal to each other, we know exactly what has to happen for this to work. What has to happen?
Let them equal to each other?
The exponents have to equal each other. So 2y has to equal 1. So y equals 1/2. Can I check my work? Of course. I'm trying to find log base 16 of 4. Nope, no problem at all. I never use this, but I'll show you. I think it's, what is it? Log base A. Here it is. And the base is 16. And the number is 4. And the answer better be 0.5. Because the square root of 16 is 4. 16 raised to the square root, in other words, raised to 0.5 equals 4. As expected. Good. Do we need another example? Or we move on to compound interest? This 29 looks very interesting, but how much is log base 8 of 8? I couldn't hear you.
Just 1?
Yes. How much is log base 3 of 1 now? Because this is 1.
Oh.
Indeed, it's 0. Exactly. It looks fabulous. Nothing. Log base 8 of 8 is 1. Log base 3 of 1 is 0. Log in any base of 1 is 0. Good. Anything else from 14 through 28?
Can we just do 18?
Of course. Let's look at 18. 18, I see it. In 18, we have 13 raised to y equals 874. Good. I don't care what this is. I'm writing my formula. Log base a of x is y is equivalent to a raised to y equals x. But now this is on this side. So I have 13 raised to y equals 874. I have a log, I have to have a base, I have to have a number here, and I have to have a number here. And I know exactly how I start. This raised to this equals this. So what do I put here?
13.
Of course. What do I put here? From here.
But why?
Exactly. And of course, what is left for this?
$8.24.
Of course. That's it. Now, if they're asking us to solve this, I have to see if 874 can be written with a base of 13. So I don't know if they're asking us. They're not, but that's okay. So 13 squared. 13 to the third. It's already too much. No. 874 cannot be written with a base 13. That's why they're not even asking us to find anything. Good. They're only asking us to write the equation in its equivalent log form. And that is log base 13 of 874 equals y. Do we need anything else from here, or I'd like to finish up tonight with investments, the compound interest formulas for 10 and 11. And that's the whole review. We have to look at another graph or two graphs to make sure that, and that's it. That's the whole thing.